Alright, picking this up. So we're going to throw the rest of the logic in these other functions here. Flag infinite karma 0. If it's equal to 0, then just go to remove or process remove point in character creation. Otherwise, it is not equal to 0, and we are going to assume that that is the user attempting to enable the cheat. So we will jump to cheat remove point cc. So you may be asking yourself at this point, is it wise to have all these entry points for all these different things? And generally you won't run into this. I mean, it's not a question of wisdom per se, but it's just the way that we built the script up originally. And again, I mean, this game has 4 different routines or whatnot for modifying the karma value, 2 for adding the during character creation, removing during character creation, adding in game, and removing in game. You just I find that I don't usually deal with that. Usually it's just one function that modifies the value, and then it just passes in some parameters like a 5 or a -5, depending on whether you're adding or removing points. And in that sense, you will just usually have one entry point where you can just say, hey, is it enabled? Then I want to go here. And then if it's not enabled, I want to go here. It just the way that the game is, then this is just how this is a result of how we set it up initially and how the game itself is set up. We could probably go back and rework the logic and maybe cut down on some of the redundancy here, but we're not going to do that, or at least we're not going to do it right now. What's that? Spend point in game, and then if it's not that, then it's 1. So we want to jump to cheat, remove, or spend point in game, and then we're going to go to compare flag infinite karma 0, and then if it is 0. If it is equal to 0, then we will jump to just process remove point in game, and if it is not equal to 0, then that is the user attempting to enable the cheat, so we will jump to cheat remove point in game. It is worth noting as well that you could reverse the logic here. You could just, instead of comparing it with 0, you could compare it with 1, and then you could come over and say, well, what conditional jump can I use? I want to say it's jump if greater than or less. I don't know. You could work it all out, but JNE, I guess, is what you could probably do. But I don't know. I find it just, you compare it with 0, and you default. I generally default to the cheat is disabled, because that's how the script is when we first push it. When we initialize this flag, it's disabled, and then if the user has changed this value, then we will jump. So I don't know. That's just how I do it. It makes no difference. Again, if you made this 1 and then said, I don't know, JNE, say, well, if it's not equal to 1, then, go jump to, you would have to reverse it as well and make this, do you have to do that? No, you wouldn't. So compare flag infinite karma to 1. If it's not equal to 1, then we are going to interpret that as the cheat is disabled and go jump to process spend point CC. And if it is not 1, then we will interpret that as the cheat is, or if it is 1, then we will say, oh, that's the user enabling the cheat, and we will jump to cheat spend point. But I don't know. I just do it. I compare my flag to 0, and then if it is 0, then I go to whatever the game would normally do, the original code, if you will. And then if it is not 0, then I interpret that as a true value, and that is a reflection sort of just how I am when it comes to Boolean data types. And again, I don't know. I'm not going to bother with it, but you could certainly, there's a link. We'll just click it. Let's see. Truth value. Can we maybe get that a little bit? C, C++, Perl, stuff like that. It's not. I don't know. I'm not going to deal with it. But basically, in most programming languages, if the value of something is 0, then it is false. And if the value of something is non-zero, whether it's -1 or 1, it's not just greater than 1. But if it is not 0, then it is true. Which means, for me, in this context, it's compare this to 0 so that this flag would be false, and then I want to go here and do the normal code. And then if it is non-zero, then the cheat is enabled, and I want to go here and I want to do that. So again, that's just how I function. You can reverse it if you want, but then you're, again, I don't know. I'm going to stop talking about it because it's doing nobody any good at this point. So let's just think about this real quick. we have all this stuff for character karma and blah 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 blah. We're making that 0, and then we're comparing flag infinite karma. Let's talk about brackets in the context of cheat engine. Are we hooked up to anything? No. We're going to go to, we'll stick with Firefox. That's a decent, um, that's just, I don't know, it's decent. So if you are following through the assembly instructions, and I'm sure you've asked yourself by now, why are some things in brackets and some things are not in brackets? And we can go to the cheat engine forums, or let's not even do that. Let's just say, not even really specific to that, but let's just say assembly language brackets. What do brackets mean in x86 assembly? Given the following code, db something 0, move al l1, move eax l1, what do the brackets L1 represent? L1 means the memory contents at address L1. After running move AL open bracket L1 close bracket here, the AL register will receive the byte at address L1, which is the letter W. Thank you for your reply. It's always a way to do it. Let's keep reading. The brackets, simply, if I may editorialize here, simply mean to get the memory at the address marked by the label L1. So in our sort of series here, let's talk about that. What do brackets mean? It means to get the value at the address marked by whatever is in between the brackets. No, that's not what I want to do. I want to do that. So when you open up the memory viewer here and you're reading through it, what is EAX in this case? Or I'm sorry, what is EBP plus 08? It is whatever the memory location of EBP is, or is stored in EBP, as the case may be, and then I want to add 8 as an offset to it, and then I want to just basically, I want to evaluate EBP plus 8 first, and then I want to go to whatever EBP plus 8 is, as we demonstrated with the offsets in our own script, and then I want to dig out the value of that memory location, and that is how basically what the brackets do. And you can see up here, maybe, here's a compare. It is comparing ECX with whatever the value of the memory location firefox.exe plus 5018 is. It's not comparing the actual memory address of firefox.exe plus 5018. It is going to firefox.exe plus 5018, and it is digging out whatever value is stored in there. How does it know how big that value is? That is a good question, and that is something that we will get into in a little bit. But for our purposes, let's just say that it knows it, or that there is some relation between the first parameter and that. There's some relation between the size of the first parameter and how much memory, how many bits it's reading in the second. But again, the brackets is telling it, go to whatever Firefox.exe is, and it's some value, some memory address, and then add 5018 to that address, and then read some amount of bits and convert that to some value and compare that to the register EAX. Let's see if we can find another somewhat decent example. Yep. So you can see the brackets here are not just limited to the second operand. You can say I want to do a move. I want to move the value of EAX into whatever is stored in EBP minus 1C. So how come you don't have to put brackets around EAX as a value or as a register, but over here EBP is also a register and you have to put brackets around it? Because brackets are essentially a way of telling the processor, hey, I'm dealing with memory, not values, or quite the opposite, as the case may be. Depending on the context in which you're using the brackets, you don't really have to put brackets around EAX in this scenario, because it's just the EAX is a register and there's some value in EAX, and it will just go to the register EAX and say, yo, what are you hiding? What are you sitting on? And EAX will just be like, well, I got some value. And it's like, great. And then it will just take that value, and then it will go over to EBP in order to complete the move instruction. It'll go to EBP and say, or first it's going to encounter the brackets as the case may be, and then it's going to go to EBP and say, well, I'm dealing with memory, so whatever the value in EBP is, I'm going to read that as a memory address, and then I'm going to subtract 1C, and then I'm going to take whatever EAX coughed up, and I'm going to stuff it in that address, and that's how I will complete this instruction. Let's see if we can go. Let's go back here. See if we can just search for bracket. So let's read this. Whenever you see an opcode with two parameters, the first parameter is the target of the instruction, the second is the source. Sub ESI plus 13 EBX. What is EBX in this case? It is something, and ESI is something else. In this case, you see the first parameter is between brackets. This indicates that instead of registers, a memory location is being used. That's more or less what we just said. The memory location is pointed at by what's in between the brackets. In this case, ESI plus 13. Note that the 13 is in hexadecimal, obviously because we're dealing with assembly. So is brackets mentioned here? Note, it's really useful to understand how those values between brackets work, because then you can make the most use of pointer stuff in CE 4.1. I really hope you're not using 4.1, but whatever. It will remove for most games the dynamic memory allocation problem if you know how to look at the assembler code that accesses the values you found. Not going to worry about that. Let's do that. Let's go here. Where's brackets? Where's the word brackets? There we go. The brackets, open and close, are used to get a value from the memory location between the brackets. Without brackets, it is just a value. A register as memory location is allowed to, it should be 32-bit and 32-bit programs. There's that and that. The processor looks what's about. All right, so move EAX, some hexadecimal thing. Make EAX have the value 403054 or 045 in hex. And then if you look at the next instructions, move EAX in brackets into CX. Put the word size value at the memory location EAX, which is 403045, into register CX. That's not really that clear, but basically in move CX, open bracket, EAX, close bracket, the processor first looks at what value or memory location EAX holds, then what value is at the location that it just dug out of EAX. And we'll put that value into CX. And this is essentially how pointers are implemented with via registers and things like that. If you haven't figured out, or if you haven't connected the dots at this point, then basically the brackets are just saying, hey, I'm dealing with pointers and memory addresses, and so you have to tell the processor, you have to be able to differentiate that kind of stuff to the processor, and brackets is basically how you do that. Another special notation that the change value field supports is change value. You can rearrange items, yada yada yada. I'm not gonna worry about that. Brackets, very important. So where's our script? Here it is. So that's why we are putting this in brackets. We are saying I don't care, because if we did not put brackets around it, what it's going to do is it's just going to say compare whatever the memory address of flag infinite karma is with 0. And the memory address of flag infinite karma is never going to be 0. It's always going to be some location, virtual, physical, whatever you want to say. So by putting brackets around it, we are telling the compare instruction and the processor more specifically, get the value of flag infinite karma, but it's a pointer. So I want you to go to that address, and then I want you to dig out the value of that. And then I want you to compare that value to 0. And again, this is why we talked about pointers endlessly as like 15 videos or something like that. Because when you are dealing with pointers, even in like C++ and some languages like that, there are some facilities that make it a little bit easier for you to deal with this stuff. When you drop down to assembly and certainly dealing with this kind of stuff, if you don't understand pointers in a fundamental way, then you're going to be bouncing around in memory, and you're going to wind up in the wrong spot. You're going to crash your game. You're going to crash some other programs, and you're never going to be able to figure out why. And odds are it's because you either have brackets when you don't need them, or you have brackets or you don't have brackets when you need them. So go get the value of flag infinite karma, compare it with 0. If it is 0, jump to process spend point CC and pretend that the cheat is not enabled. even though the script is, we will just act as if the cheat is not enabled. Then we will, if it is a not zero, if flag infinite karma has a non-zero value, we will jump to cheat spend point CC, which is right here, and we will move 100 into EAX, and then we will jump to the spend point of the process, and we will go there. So let's hit OK. Basic syntactical check of cheat engine says you're good to go. Everything seems copacetic. So let's start up the game. Go to continue. We will harp more on the brackets as we go through some more of this stuff. Not in as lengthy detail as I just did right now, but it's important to understand the distinction. So we want to do that. Nope, that's not right. We want to do that. So let's attach to the right process this time and not try and enable a cheat on Firefox like I did in a previous video. So we want to do that. So let's enable our karma script. I hit plus, I hit minus, so that crap's in memory. That code is in memory. There you go. Our flag snaps to and says, yep, I got an address. The value is 0. So let's go in here. We'll hit plus, we'll hit minus. Why do we have 100? That's interesting. Am I that stupid? Did I screw up the logic that much? So compare that with 0. If it is equal, then jump to process spend point. If it is not equal. It should not be doing that. I gotta stare at this and think about it for a second. Let's change that to 1. Let's hit plus, let's hit minus. We're still getting 100. Alright, so there's maybe not the flag error. It's probably just some logical error in the script. So we are doing a compare with flag infinite karma 0. So we're saying if this value is 0, then jump to this. And if it is not 0, then jump to that. We are initializing that value to 0. And obviously that's all good. So let's do that. Let's disable it. Hit that. All right. So now everything's working. So now we're going to go back in here and re-enable the script. All right. So now it's that. And if we change it to 1 just to double check it, we can do that. So it doesn't seem to matter what the value of the flag is. So we obviously screwed something up. You know what we screwed up? I already know what it is. It's actually probably a good thing that we just screwed that up. So here's what we have to do. We have to do this. So what does that mean? What it means is basically we're going to introduce the concept of words and double words. We've sort of gone over them a little bit. Well, first, let's just prove the point. Let's say, yes, this is actually the solution to our problem. Let's just cut this out to make it a little quicker. So there's that, and then there's that. Hit yep, disable it, re-enable it, and then flag infinite karma will take that. It is 0. We'll hit plus, minus. Oh, look at that. You hit plus, you hit plus. Now it's subtracting it. It's like the cheat doesn't even exist, kind of like it was supposed to from the beginning. So now let's not do that. But we will go back here and say flag infinite karma is 1. Now the cheat is enabled according to our script, and now we can't really mess with karma, whether we add or subtract a million times. So let's disable it. What is byte pointer? When you are dealing, and again, we're about to introduce word sizes and stuff like that. We've sort of skirted this issue as much as possible. So let's just say word computer architecture. Let's check Cam Studio. We're getting on there. So what is a word? In computing, a word is the natural unit of data used by a particular processor design. In our case, x86. Or a 32-bit is probably a better way to say it, or 64-bit, or whatever. A word is a fixed size group of bits that are handled as a unit by the instruction set and or hardware or the processor. Handled as a unit. The number of bits in a word, the word size, width, or length, is an important characteristic of any specific design or computer architecture. Modern processors, including embedded systems, so let's skip that. Modern processors usually have a word size of 8, 16, 24, 32, or 64 bits, while modern general purpose computers, which is what we are dealing with here, usually use 32 or 64 bits. The size of a word can sometimes differ from the expected due to backward compatibility with earlier computers. So what is the use of words? Depending on how a computer is organized, units of the word size may be used for integer numbers. Holders for integer numerical values may be available in one or several different sizes, but one of the sizes available will almost always be the word. The other sizes, if any, are likely to be multiples or fractions of the word size. Floating point numbers, no addresses. This is mainly what we're going to talk about right here. Holders for memory addresses must be a size capable of expressing the needed range of values but not be excessively large. So often the size used is the word, though it can also be a multiple or fraction of the word size. Unit of address resolution. In a given architecture, successive address values designate successive units of memory. This unit is the unit of address resolution. In most computers, the unit is either a character, a byte, or a word. What is the word? Well, it's the word size of the computer, which generally, as we are saying, is 32 or 64. A few computers have used bit resolution. That's nice. If the unit is a word, then a larger amount of memory can be accessed using an address of a given size. And that's all we're going to read about that. Let's see here. So basically, when you are dealing with a 32-bit machine or a 32-bit word size, and there is a lot of subtlety here because I'm using a 64-bit machine, but yet my word size, sort of when I'm screwing around with this stuff, is sort of defaults to 32-bit. So even if you're running a 64-bit machine, don't think 8 bytes. Think 4 is sort of the default size. And in the case you have an interest in this stuff, you could maybe let's do 32-bit. You may have heard about it. This is sort of an A-side, but you may have heard that, well, you can only use 4 gigs of RAM in a 32-bit machine. Why is that? Well, it's because the memory addressing in machines is based on the word size. And if the word size of a processor or an architecture is 32-bit, then it cannot address, or generally speaking, it cannot address memory higher than whatever the value that you can store in 32 bits is. As it turns out, the max value of a 32-bit or of a 32-bit integer is some fucking huge number right here. Hence, a processor with 32-bit memory addresses, or more specifically in our context, a processor with a 4-byte word size or 32-bit word size, can directly access 4 gigs of byte addressable memory. That's where that limitation comes from. And if you go look up 64-bit, you can see that they can hold all kinds of crazy stuff. But, why did we make this A-side? It's sort of to prove that we're not crazy. So, again, even if you're on a 64-bit machine, think 4-byte memory addresses, because what you're dealing with when you're moving pointers and memory addresses around is that the computer is going to default to its native word size, and most of the times these days it's 32 bits or 4 bytes. So we have to qualify. So if we get rid of the byte pointer right here, what's happening is that the processor, we're not qualifying this statement at all. We're just saying, hey, do this compare. And similar to what we did with the notepad in a previous video or somewhat recent video, that's 16, that's 32. What the computer is going to do is it's going to be, oh, okay, so I'm not being qualified by anything, so I'm just going to do a comparison. Well, I'm going to compare the 32 bits in whatever flag infinite karma is with 0, and I'm going to interpret 0 as a 32-bit value. So what we have to do is tell the computer, no, 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 no. Stop using your native word size, and basically, what you are comparing is a 1-byte or 8-bit value, and then the size of the second parameter will be relative to the first. So if you qualify the first one, or just basically if you qualify the instruction with byte pointer, then the processor and by association cheat engine is just going to be like, all right, so I'm doing this. I'm comparing some location with some series of bits, and I'm only doing it in 1 byte. No, I don't want to save it. So let's see if we can maybe generalize what is a word size. A word size is the default size in our context here. The word size of a computer or an architecture or a processor, we're not really making any distinction at this point, is the default size of memory addresses in the system. So that when you are saying to a processor or a computer, are we still hooked up? Yeah, I guess we are. I don't know. Let's go way the hell out there. That's probably not a good idea. Anyway, so when you say to a processor, hey, I want to go to a memory address, or just looking over here at the addresses over here, let's use our knowledge of hexadecimal and bytes and things like that to maybe sort of deduce this a little bit. What is a hex digit? A hex digit is 4 bits. So we know that 2 hex digits represents 8 bits and 1 byte. So if you look at the memory address here, you have 2, 4, 6, 8. You divide that by 2, you get 4 bytes. Is that an accident? No, because this memory address is 4 bytes. This is sort of, again, I'm on a 64-bit machine, but it almost doesn't even matter. For our purposes, it doesn't even matter. And so that's 4 bytes. That's 32 bits. That's the native word size. And that's how memory addressing is stored. They're really just numbers. There's no sort of distinct memory address type. It's more just, hey, it's just an integer. And then that integer is applied to, via a series of offsets similar to what we are doing in our script with this kind of stuff. It's just an offset relative to an offset relative to an offset, yada, yada, yada. And eventually it's just indexing into the physical absolute memory RAM of your computer via a memory management unit, or an MMU, which is we talked about in a previous video, or at least I think we did. And that's how this sort of translation is done. So we may come back and harp on this a little bit more. But basically, when you hear the phrase word, think 32-bit, because you probably couldn't even watch a YouTube video on a 16-bit machine. And if you're on 64-bit machines, then unless you have reason to believe otherwise, just think 32 bits and 4 bytes anyway. For our purposes in this series, that's what we're going to say. And I can almost guarantee we're going to have to come back and revisit this topic, because I probably have done it no justice, and it might be a little embarrassing when I go back and watch the video, but that's why we have to qualify this with byte pointer. And why do we have to throw in pointer? Because we're dealing with a pointer. We're saying, hey, there's some flag infinite karma is some address, and just, stop treating it as a 4-byte memory address or a 4-byte value, and just say, there's a pointer, and here is that memory or there's a memory address. It is flag infinite karma. We surround it in brackets. It says go get that value, and then we say treat it as 1 byte, and then it will compare 0. Basically, what it's really doing is it's saying what is 0 in an 8-bit pattern. It is 8 bits, but we can just use 1, and then it will say, okay, compare 0 to flag infinite karma as a byte, and that's what the bug was in our script. And I'm going to stop this, and we'll come back and pick this up.